Now for numbers 4 and 5, which are quite similar, as you can see, these are, you could say, so-called implicit differential equations. What the implicity about them, what's behind it, is the fact that the functions described in these equations, which are also, of course, the solutions afterwards, turn out to be, well, yeah, usually described as implicit functions, which means that there is a certain equation defining this coupling between x and y, and there's no way of telling y to be a single term of x. In this case, in these two cases, it will be possible, well, to sorry, to write down two different functions, one for the upper half and one for the lower half of the graph. So that's possible. But anyway, they are quite interesting for certain reasons, because they describe very famous kind of curves. Now let's see. And then we should also add a short geometric interpretation of the results. So that's what we try and do. And this starts here, where we look at this number 4, which tells us that y times y prime equals x for any value of x. And here I give you just a short hint at how it's usually, the form in which an implicit function is usually given, namely as a term of both variables x and y set to be some constant. You remember this, and it's even an examination topic. Don't forget it. It's the so-called implicit derivative, which you can take. So it's even possible to, you could say, to differentiate an equation on both sides, but then you must be careful also knowing everything about partial derivatives, for x, for y. It depends what you're doing. Okay, but we don't talk about this right now. So this is just a hint. And look here. Now, transforming as usual this to be a differential quotient, dy over dx, then taking everything times dx, so that we have x dx on one side and y dy on the other side. It's quite nice and simple. If we take an indefinite integral on both sides, we get the primitive here for y, of course, which is y squared half. And on the other side, it's x squared half. As always, we need an additive integration constant on one side. Now taking everything times 2, because this doesn't seem to play any important role, we may even put it in this form, so that y squared equals x squared plus renamed constant, right? So 2 times c1 is just renamed to be c in order to have a simple constant. And then, just for the reason I explained, since this is typically written as an implicit function, we subtract x squared on both sides, and so we get that the square difference, y squared minus x squared, equals constant. And this is a very famous equation. It's called the hyperbola equation. Well, it's not, more exactly speaking, it's not the most general form of an hyperbola equation, actually, but you could say it's the usual form for such a hyperbola, which is not scaled well, it may be scaled. You see, by different choices of c, you will get a different scaling of the curves, but at least it is not scaled in a nonlinear way. It's scaled proportionally on the one hand, and it does not contain any rotation to the main axes. So that's some facts about it. But if you don't recall it, you just imagine instead of the minus sign, you would have a plus. And in this case, you suddenly recognize it to be a circular equation, right? A circle equation. And so this is very, there's a very strong relation between circles on the one hand, circles with ellipses as non-linearly, as we have talked about, stretched or squashed versions of circles called ellipses. And then on the other hand, hyperbolas containing of 2 branches. Well, that's what it's all about. So anyway, this equation, let's take the unit hyperbola, which is of course the most important case. And it would look roughly like this. This is not a nice sketch, I really must say. This is just a very rough sketch. To find out roughly how the graph will look like, you may perform a test, the following test. Look, the point with coordinates 0 and -1, 0 for x, -1 for y, just inserting here. You find if y equals -1, I get -1 squared, which is 1, and then -0 squared, the result equals 1. So it's fulfilled. On the other hand, if I take this point Q here with coordinates 1, 0, I would get 0 squared minus 1 squared, which is -1. So this is not part of the graph. Neither this nor this point are. So it means the whole x-axis is to be excluded. And please don't forget, there is, of course, there are other versions. For example, x squared minus y squared equals 1. This would be the unit hyperbola of the other kind, where the whole graph is rotated for 90 degrees, so that, you know, what I'm talking about, it roughly looks like this, 2 branches, okay? So, but also there's a striking similarity to a circle, because a circle, especially the unit circle, would look like this, and we have 2 common points here, which is important. So you could say using the hyperbola, well, let's take this away. You will, starting from here, you will take a left curve, while using the circle equation, you will have to take a right-hand curve, is right? And that's because it depends on whether there's a minus sign or a plus sign here, which is taken into account in order to still fulfill the number that's given here. So it's quite easily, if you take your time, quite easily understood how these graphs come about. That's what I wanted to tell you. Well, okay, sorry. Put it away. Now, going on. So what we really found is, this is what I wanted to give you as a geometric explanation, is putting this differential equation in a slightly different form by dividing just by y now. We get this one, which says that y prime equals x over y everywhere for every point on these 2 partial graphs. And it's a fact that really the fraction, which is, yeah, it's just the relation between the x and the y coordinate of a point on one of these curves is equal to the local slope of the corresponding curve. Do you see here? This is just a tangent roughly drawn inside, and here the derivative would be positive, clearly to be seen. It's a rising graph at this point, and then inserting the coordinates of the respective point here, which is not really given, would be positive x over positive y, and this would be a positive result anyway, at least, okay? But you can check more clearly and find out, this is exactly what defines the hyperbola, actually. So that's a fact, but I just wanted to give you a hint at these things. Now, the fifth one is even, you could say, easier. At least it's more familiar, because this time we have y times y prime equals negative x, and doing much the same as before, just keeping this minus sign in mind. So we get here the primitive function is y squared half, and here this time it's negative x squared half plus some constant. Again, we can well, shuffle these terms a little bit around and then take everything times 2. So we get a very nice form, which is squared sum x squared plus y squared equals constant. And this is very often instead to be given as r squared, some r squared, which just tells you this is a positive constant. And also this little r, this lowercase r, denotes the radius of a sphere around the origin. So this is the very well-known circle equation with a circle that has its center in the origin, of course, and for middle, okay, center. And well, and r squared equals c. And you must see, or we must agree, that although this constant may be chosen arbitrarily, so it could also be negative, in case of a negative constant, we will not even have a single point as the solution. So the solution will be the empty set, which is not a contradiction to the differential equation. It just means that there are some solutions which don't, you could say they don't even exist, right? And the very special case of C equals 0 would mean that just the origin, you could say, as a sort of a singularity. It's like a circle that has been shrinked to zero size, to zero size, sorry, and this would be the solution. So, and we agree that also this singular solution is not really, probably it's not even valid, because the local slope along this shrinked circle would at some, well, would not no more be well defined. So please don't care about these exotic cases. The most interesting case is a positive constant, right? And here you see, just for the geometric aspect, a similar equation as before. We can say that the slope on any point on the circle, around the circle here, is always equal to the negative proportion of the x coordinate with relation to the y coordinate, right? So, and you can easily see this in the example for a point which is on the bisector line here. The point B might, for example, have a 45 degrees angle. You know what I mean? It would have x and y coordinates equal. And in this case, we would get y prime equals negative x over x, which is -1. And as we see, this is almost the definition of a circle, namely the fact that the tangent is perpendicular to the radius. Okay, so that's what it is. Definitely here I would have a slope of 1, but then it means that this one must have a slope of -1, and this would be the official y prime at this position. So the geometric explanation for all this is relatively clear.